July 2025. An ordinary night for sky surveys, until a speck racing at over 130,000 miles per hour triggers every alarm. NASA's latest image of 3A/Atlas isn't just a pretty picture, it's a warning. A coma made almost entirely of carbon dioxide, with nearly no water vapor so bright it defies physics. The official science behind comets just collapsed. Today, new image of 3I/Atlas changes everything, isn't hype. Why does this interstellar visitor break every rule in the book? And what did NASA really discover that they waited to reveal? The deeper you look, the stranger it gets. The Atlas Survey telescope in Chile picked up the first hint of 3I/Atlas just after midnight on July 1st, 2025. The object registered as a faint, fast-moving blip, magnitude 18, hurtling through the star-crowded sky at more than 130,000 miles per hour. Its position, 670 million kilometers from the Sun, put it well beyond Mars, deep in the outer solar system. But what caught the Atlas team's attention wasn't just the speed or trajectory. Even at this distance, the object wasn't a cold, silent rock. Early images revealed a diffuse glow, a coma surrounding the nucleus. Larger telescopes quickly confirmed what the survey data hinted. 3I/Atlas was already active, its coma stretching outward in a teardrop shape. This wasn't just a rare interstellar visitor, it was a comet waking up far earlier than expected. David Jewett and Jane Liu, using the Nordic Optical Telescope on July 2nd, reported a clearly active, extended object. Simultaneously, the Tide Observatory's team in the Canary Islands saw the same diffuse appearance. The coma's reddish hue, measured at 18 plus or minus 4% per 1,000 angstroms, suggested dust dominated the early activity. But there was a problem. At 4.5 astronomical units from the Sun, water ice shouldn't sublimate quickly, and yet the coma was unmistakable. Surface brightness profiles from Palomar and Apache Point showed the object's light spreading well beyond a point source, with flux levels 2 to 10 times higher than background stars outside 1.3 arcseconds. The coma's full width at half maximum measured about 2.2 arcseconds, compared to 1.6 arcseconds for stars in the same field, confirming that the glow wasn't an illusion or artifact. Archival data from NASA's TESS spacecraft, covering May and June 2025, revealed the object's brightness remained steady as it approached the Sun. Even at 6.4 astronomical units, it may have been active, with an absolute magnitude around 12.5, far brighter than a bare nucleus of comparable size. The coma's dust cross-section within 10,000 kilometers of the nucleus was estimated at nearly 185 square kilometers, pointing to ongoing dust ejection at rates up to 1 kilogram per second. Yet no gas emissions like CN or C2 were detected, a pattern familiar from distant, dust-driven comets in our own system. The trajectory was just as strange as the activity. Calculations showed a hyperbolic excess velocity of 61 kilometers per second, meaning the object was unbound, inbound, and moving too fast to belong to our Sun. The orbital eccentricity exceeded 6, dwarfing the values for both Oumuamua and Borisov. Within days, the Minor Planet Center issued its circular. This was the third confirmed interstellar object, now officially designated 3I/Atlas. Its early dust-rich coma and hyperbolic path set it apart from anything seen before. As astronomers tracked its approach, the need for deeper chemical analysis became urgent. Only space-based infrared telescopes could probe the true composition and solve the mystery of why this interstellar comet was breaking every rule so far from the Sun. On August 6, 2025, the James Webb Space Telescope trained its NIR SPEC instrument on 3I/Atlas, searching for the chemical signatures that might finally explain the comet's early activity. The spectrum that came back was anything but ordinary. Instead of the expected dominance of water vapor, the data revealed a coma overwhelmingly rich in carbon dioxide. The carbon dioxide to water mixing ratio wasn't just high, it was off the charts, 8.0 to 1. For comet scientists, this number landed like a thunderclap. Most comets at this distance show water as the main driver of activity, with carbon dioxide trailing far behind. Here, the roles were reversed, and by a factor never seen before in a comet at 3.3 astronomical units from the Sun. The NIRSpec data mapped out the coma's chemical fingerprints in fine detail. Carbon dioxide lines towered over everything else, while water vapor appeared only as a faint trace. The production rates told the same story: 129 kilograms of carbon dioxide released every second, compared to just 6.6 kilograms of water. That's not just unusual, it's a 6 sigma outlier, placing 3I/Atlas in a category of its own. The only other comet to come close was the oddball C/2016 R2, but even that object didn't match this level of carbon dioxide dominance. For the JWST team, the results raised more questions than answers. If water ice wasn't driving the coma at this distance, what was? Was the nucleus formed in an environment where carbon dioxide was the main ingredient? Or had billions of years in interstellar space altered its chemistry in ways no one had anticipated? The chemical puzzle was now front and center. With water vapor taking a back seat, astronomers needed a wider view to pinpoint the true source of the carbon dioxide and to understand how such an extreme ratio could persist so far from the Sun. The call for broader, wide-field imaging was immediate. The mystery had shifted, from the orbit to the chemistry itself. SPHEREx turned its wide-field infrared gaze toward 3I/Atlas in early August 2025, capturing a scene unlike anything seen in cometary science. Over 4 nights, the spacecraft mapped the comet's surroundings across the near-infrared, revealing a ghostly envelope of gas stretching farther than the distance from Earth to the Moon. The carbon dioxide coma measured an astonishing 348,000 kilometers in radius, nearly the size of Jupiter. This wasn't a faint haze. The emission dominated the field, dwarfing the nucleus at the center. SPHEREx's detectors, designed to catch the faintest molecular signatures, lit up with the unmistakable fingerprint of carbon dioxide. The team's preliminary analysis showed that every pixel in the long wavelength images was saturated with this molecule's glow, while shorter wavelengths, where water vapor would normally appear, remained eerily quiet. The sheer scale of the gas envelope forced a rethinking of cometary activity. No known solar system comet has ever produced a carbon dioxide coma on this scale, especially at 3.2 astronomical units from the Sun. For the SPHEREx instrumentation group, this was a technical triumph. Their mission, built to scan galaxies and cosmic ice, had just delivered the most expansive map ever made of an interstellar comet's gaseous shroud. The data showed that the coma's reach extended well beyond the field of view of most telescopes, confirming that what looked like a modest point source in visible light was, in fact, the heart of a vast, invisible cloud. The enormity of the carbon dioxide envelope set the stage for the next puzzle. What could possibly drive such an outflow, and why was water vapor so conspicuously absent? SPHEREx images captured a spectacle that left even seasoned comet scientists scrambling for explanations. The carbon dioxide envelope surrounding 3I/Atlas wasn't just large, it was overwhelming, stretching hundreds of thousands of kilometers in all directions. But the real shock came from what wasn't there. Across the entire near-infrared spectrum, the usual fingerprints of water vapor were almost entirely absent. Instead, every pixel in the long wavelength images was saturated with the glow of carbon dioxide. The mass loss rate told its own story. Nearly 70 kilograms of carbon dioxide escaping every second, yet water vapor remained so faint that even the most sensitive detectors could only set upper limits. For a comet at 3.2 astronomical units, this chemical imbalance is unprecedented. In typical solar system comets, water vapor dominates the coma as soon as sunlight can warm the nucleus. Here, the expected surge of water-driven activity never arrived. The coma's brightness, too, defied prediction. Despite the massive outflow of carbon dioxide, the object's light profile remained concentrated, almost point-like, rather than spreading into the kind of broad, dusty halo that usually signals heavy mass loss. NASA's own teams found themselves at a loss. The numbers didn't line up with any known model of cometary behavior. A carbon dioxide coma this vast, with so little water vapor and such a compact appearance, forced a reckoning with the fundamentals of comet science. The familiar rules, how sunlight drives activity, how dust and gas shape a comet's glow, no longer seemed to apply. With each new frame, the data pressed a single, urgent question. What kind of object produces this much carbon dioxide, but leaves water vapor behind? Astrophysicists have put forward two competing ideas to explain how 3I/Atlas ended up with such a bizarre chemical fingerprint. One theory starts with radiation, billions of years spent drifting through the galaxy, bombarded by cosmic rays and ultraviolet light. Over time, that radiation can break apart molecules like carbon monoxide and water ice, then recombine them into carbon dioxide. Laboratory experiments back this up. Expose carbon monoxide and H2O ices to high-energy particles, and carbon dioxide forms efficiently. If 3I/Atlas has truly wandered the interstellar medium for up to 11 billion years, as its thick disk galactic orbit suggests, it's had ample time for this kind of molecular remodeling. The other camp focuses on where the comet first took shape. In the outer reaches of a newborn planetary system, temperatures drop low enough for carbon dioxide to freeze out of the gas phase, a region called the carbon dioxide snowline. If 3I/Atlas formed right at this boundary, it could have locked in more carbon dioxide than water from the start. That would naturally explain why carbon dioxide dominates its outgassing now, even as it approaches the sun. The thick disk connection hints at an ancient origin. Stars and planets from this population formed when the Milky Way was young, between 3 and 11 billion years ago, under conditions that likely favored different ice chemistry than what we see in our own solar system. Both scenarios carry weight, but neither can fully account for every detail. Some researchers point to the comet's galactic age in thick disk orbit as evidence for deep time radiation processing. Others highlight the chemical fingerprints that match what you'd expect from formation at a carbon dioxide-rich snowline. With only a handful of interstellar objects ever studied, each new data point forces astronomers to revisit old assumptions. The next round of observations will be crucial for sorting out which process, radiation alteration or birthplace chemistry, left the biggest mark on 3I/Atlas. Even with a coma stretching hundreds of thousands of kilometers, the numbers still refuse to add up. The carbon dioxide mass loss, measured at 70 kilograms per second, should have produced a far brighter and more diffuse coma than what SPHEREx and JWST actually recorded. Instead, the visible light profile stayed stubbornly compact, almost point-like, while the infrared map showed a vast but faint envelope. Photometric models, run by teams at Palomar and Apache Point, calculated that if all the near-infrared flux came from a bare nucleus, the radius would have to be about 23 kilometers. Hubble's high-resolution imaging, however, set the maximum at just 2.8 kilometers. That means more than 99% of the measured flux must be coming from something other than the nucleus. NASA's spokesperson described the mismatch as a classic mass loss versus luminosity puzzle. The dust and gas pouring off 3I/Atlas simply don't scatter enough light to explain the observed brightness. At the same time, the upper limits on water vapor, 1.5 times 10 to the 26th molecules per second, according to SPHEREx, sit well below the levels seen in even the most sluggish solar system comets. Researchers have combed through the data, looking for overlooked emission lines or hidden dust populations, but the anomaly persists. The peer review process has only added to the uncertainty. With such a wide gap between expected and observed luminosity, every new dataset is scrutinized for calibration errors or instrumental quirks, yet so far, the results hold. As 3I/Atlas moves behind the Sun, astronomers are left waiting for the post-perihelion window in December 2025. when the comet will reemerge for another round of scrutiny. Until then, the true source of its brightness, and the reason for the delayed release of these images, remains an open question. On August 8, 2025, NASA's SPHEREx mission captured an image of 3Pari/Atlas with a coma stretching 348,000 kilometers, composed almost entirely of carbon dioxide, not water vapor. The JWST had already flagged the object's carbon dioxide to water ratio at 8:1, far beyond any known comet. Yet 3I/Atlas continues to shine much brighter than its measured mass loss can explain. Even after months of analysis and the public release of SPHEREx data, NASA scientists have no consensus on the cause of its waterless eruption or its unusual brightness. Theories about radiation processing and ancient galactic origins remain unproven. Key technical documents and images were held for peer review, delaying answers. As 3I/Atlas moves beyond perihelion, new observations are scheduled for December 2025. The facts are clear. This interstellar visitor challenges every model of comet science to date, and many of its secrets remain locked in the data.